My name is Jasmine Lagier, and I'm presenting my work on multimodal neuroimaging classification of Alzheimer's disease using interpretable graph attention networks. Alzheimer's disease is characterized by extracellular amyloid beta plaque deposition, intracellular tau neurofibrillary tangles, progressive cerebral atrophy, and functional connectivity disruption. These pathological processes unfold across multiple biological scales. Different modalities capture complementary pathological processes. Functional MRI reveals connectivity alterations preceding structural decline. Structural MRI quantifies gray matter atrophy. PET imaging captures molecular pathology through amyloid and tau tracers. Genetics provide ApoE risk stratification, and demographics include age and sex as non-modifiable factors. The clinical challenge is integrating these heterogeneous biomarkers while maintaining clinical interpretability for diagnostic decision support. My investigation of the literature revealed three critical limitations in prior approaches. First, black box architectures achieve high classification accuracy but provide limited clinical interpretability. Second, feature concatenation methods neglect brain network topology, losing spatial relationships between modalities and failing to model connectivity mediated disease propagation. Third, single modality models provide incomplete characterization of Alzheimer's pathophysiology. This leads to the following research objectives: to develop an interpretable framework for multimodal classification, to integrate functional connectivity, structural atrophy, molecular pathology, and genetic risk within a unified architecture, to provide interpretability, and to validate decisions against neuropathological staging criteria. For this project, I used data from the Alzheimer's disease neuroimaging initiative. The dataset included 560 neuroimaging sessions. Each brain was represented as a weighted undirected graph. Nodes represent 112 brain regions, edges represent functional connections, and edge weights quantify the connectivity strength. The key innovation is broadcast node feature engineering. Each node receives an identical feature vector. The graph attention network consists of three layers. Layer 1 uses 4 attention heads with 64 channels with batch normalization and ELU activation. Layer 2 maintains this configuration with 50% dropout for regularization. Layer 3 uses a single attention head producing 64 dimensional embeddings. Classification uses global mean pooling followed by a fully connected layer projecting to two classes, cognitive normal and Alzheimer's disease. Five-fold stratified cross-validation with participant level splitting prevented data leakage. Interpretability analysis included systematic ablation studies comparing baseline, PET added, SMRI added, and full multimodal models. Feature-level attributions used integrated gradients. Region attribution computed attention-based scores quantifying each region's contribution to classification. Results showed the full multimodal model achieving AUC 0.92. Ablation studies demonstrated multimodal synergy. Compared to prior methods, my approach achieved 1.4 to 4.4 percentage AUC improvement over state-of-the-art CNN approaches. Critically, this performance was achieved with intrinsic interpretability via attention mechanisms rather than post-hoc explanations. Regional attribution demonstrated perfect concordance with Bragg neuropathological staging. One of the most valuable insights emerged from quantifying how the model uses different modalities through integrated gradient analysis. This hierarchy is profoundly meaningful from a biological perspective. The model independently learned what clinical neuroscience already knows, without explicit supervision, validating that the framework captures genuine disease biology rather than statistical artifacts. To conclude, I will synthesize the major insights from this project. First, broadcast feature engineering enabled the interpretable multimodal learning. By forcing discrimination through graph pathology rather than regional features, the attention mechanism directly quantifies interregional influence while achieving computational efficiency and biological alignment. Second, intrinsic interpretability surpasses post-hoc explanation methods. Third, effective multimodal integration requires preserving relational structure. The synergistic improvement I observed came from maintaining spatial relationships within the graph framework. The specific gap I felt is that in prior work, there was a false choice between accuracy and interpretability. This work contributes a novel broadcast engineering strategy, achieves a high accuracy, and provides biological validation. This represents a meaningful step towards applicable AI in clinical neuroscience. Models that are accurate, interpretable, and grounded in biological mechanisms. Thank you.